Hello, everyone, and welcome to this mini lecture. The automation and intelligence of agricultural product equipment has become an inevitable trend. Tedious tasks that were previously labor-intensive are now increasingly being replaced by machines. One important task in this transition is the visual sorting of irregularly placed agricultural products, such as soybeans or mushrooms. When using machine vision to sort multiple randomly placed agricultural products, a key challenge is how to eliminate the overlapping areas between individual items so they can be correctly identified and counted. By performing morphological operations on machine vision images, adhesion between agricultural products can be eliminated. This section will take the soybean counting project as an example, introducing the concept of image morphological operations and the usage of related tools through the identification and counting of disorderly placed soybeans. It will provide a step-by-step explanation of image morphological processing methods and the programming and debugging of software functions, such as blob analysis tools. This class will mainly cover two topics. First, let's understand the definition of image morphology. Image morphology is a method that uses structural elements with specific shapes to measure and extract information from an image, thereby analyzing and identifying morphological features within the image. There are four main morphological operations: erosion, dilation, opening, and closing. These tools help remove redundant structures or enhance necessary feature structures for visual inspection, all while preserving the essential form of objects in the image. What are the principles of these four processing tools? Let's now explore them one by one. First, let's understand erosion. In practical applications, morphological operations are typically applied after the image has been binarized, where features to be processed are shown in white and other areas in black. Morphological operations primarily act on the white, bright regions of an image and ignore the black areas. Erosion removes pixels from the boundaries of white areas, causing these areas to shrink inward. The result is that the bright regions become smaller than in the original image. Principles of erosion. As shown in the figure, let it be the image to be processed and be the structuring element, with the red part in B representing its origin. Iterate through each pixel of image A. Whenever a subimage matching the structuring element B is found in image A, set the pixel value at the position corresponding to B's origin to 1. Otherwise, set it to 0. The collection of all such marked pixels in image A constitutes the result of the erosion operation. Essentially, erosion identifies all subimages in A that match the structuring element B and marks the pixel corresponding to B's origin in each match. It is important to note that during the translation of the structuring element across the image, it must be fully contained within the target region. No part of B can exceed the image boundaries. Erosion's concavity-preserving characteristic. As shown, the solid line represents the original contour of the image, and the dashed line represents the contour after erosion. Erosion only alters concave corners, while convex corners remain unchanged. Convex corners remain unchanged after erosion, while concave corners take on the shape of the structuring element. If only part of an object is smaller than the structuring element, erosion may cause the object to break apart at narrow connections. If the object is entirely smaller than the structuring element, it will disappear completely after erosion. The illustration shows how erosion is used to eliminate adhesion between objects. As shown in the figure, by performing erosion on the original image and then subtracting the eroded result from the original image, the boundary of the target can be extracted. Next, we'll learn the principle of dilation. In morphological operations, dilation expands the highlighted, white areas of the image, extending the boundary points and thus enlarging the shape. The principle of dilation is as follows. First, calculate the reflection of structuring element B, denoted as B hat. The reflection of B is the set formed by symmetrically flipping all elements of B about its origin, denoted as B hat. Then, B hat is translated across image A, examining every pixel. If any part of B hat overlaps with white pixels in A, the pixel in a corresponding to B hat's origin is set to 1, otherwise, it is set to 0. The collection of all such marked pixels in image A constitutes the result of the dilation operation. It should be noted that, during this translation, non-origin pixels of B hat are allowed to extend beyond the image boundary. Now, let's understand the principle of opening. Opening uses the same structuring element to first erode and then dilate the image. As shown, this process separates two closely connected objects. An important function of opening is to remove bright regions on a dark background, smooth object contours, break narrow connections, and eliminate small protrusions. As shown, without altering the area of a black billiard bowl, opening removes the white ring-like region on its surface. Lastly, we explore the principle of closing. It is the reverse of opening. It uses the same structuring element to first dilate and then erode the image. Explore the principle of closing. Purpose. It further smooths object contours, eliminate narrow gaps and long thin crevices, remove small holes, and fill in breaks in contour lines. In summary, using these morphological tools allows us to remove redundant structures or enhance specific features required for visual inspection while preserving the fundamental shapes in the image. Is everything clear? In the next lesson, we'll move on to hands-on practice to deepen your understanding. See you in the next class.